In the darkness between galaxies, some explosions shine with a strange precision. They are not mere flashes lost in the void. They are signals. For a cosmic instant, a dead star can illuminate entire regions of space. And from Earth, that light travels for millions of years until it becomes a measurement. We call them type Ia supernovae, cosmic candles. Explosions so bright they can reveal the distance of faraway galaxies. So regular that the universe seems to leave within them a scale written in fire. But that very light which allows us to measure the cosmos is born from absolute destruction. Before the explosion, a remnant remains. A white dwarf. It is not a living star. It is the compressed core of a star that exhausted its fuel and left behind nothing but density. Matter packed to limits difficult to imagine. Carbon and oxygen locked within a structure that is small, cold, silent. From a distance, it appears stable, almost motionless. But that stability is not calm. It is extreme equilibrium. An invisible resistance between gravity, pressure, and degenerate matter. The white dwarf does not burn like a normal star. It is a stellar remnant trapped in a stability that cannot last forever. A white dwarf may seem eternal until it begins to gain mass. It can absorb material from a nearby star. Slowly, without visible explosions, without immediate violence, but deep inside, gravity keeps building up. There is a critical threshold, nearly 1.44 solar masses, the Chandrasekhar limit. Beyond that point, the structure can no longer sustain itself. The pressure that once maintained the equilibrium begins to warp everything from within. The star does not decide to explode. There is no intent. There is no warning. Only physics accumulating to an irreversible point. And when the limit is finally crossed, the detonation ceases to be a possibility. It becomes inevitable. Then it happens. The temperature rises. The pressure can no longer be contained. Carbon and oxygen begin to fuse in an uncontrolled chain reaction. In a normal star, expansion might relieve some of that pressure. Not here. Degenerate matter delays any physical relief. And during that delay, the reaction multiplies. The ignition does not stay in one single point. It sweeps through the entire star. The whole white dwarf becomes thermonuclear fuel. In seconds, a complete stellar structure releases an energy impossible to contain. There is no core left. There is no surface left. There is no star. Only a wave of light expanding into the void. The strange thing isn't just that they explode. The strange thing is that many of these explosions shine with a similar brilliance. Type Ia supernovae tend to originate near the same critical limit. The mass, the ignition, and the energy released follow recognizable patterns. That makes their brightness an observable reference. One explosion can be compared to another, measured, used as a scale. The universe, even in the midst of violent processes, maintains extraordinary physical regularities. And thanks to that uniformity, a distant supernova can be transformed into an astronomical measurement tool. Destruction becomes precision. With type supernovae, galaxies stopped being mere luminous smudges. Their distances could be calculated with a new precision. Each explosion became a reference point within the map of the universe. And by comparing many of them, something unexpected appeared. The universe is not just expanding. Its expansion is accelerating. The light from destroyed stars helped reveal that the cosmos changes constantly on unimaginable scales. Every supernova provided a measurement. Every measurement expanded the map. Thus, an explosion born within a single galaxy ended up revealing the dynamic structure of the entire universe. A terminal spark that illuminates the infinite. But distance matters. A type Ia observed from millions of light years away can be a scientific tool. A type Ea that is too close would be something completely different. The same light we use to measure galaxies could transform into dangerous radiation for a living planet. The Earth is not protected because it is special. It is protected because it is far away. And that difference changes everything. On a human scale, the stars seem remote. On a cosmic scale, some distances can turn out to be small. If such an explosion were to occur too close to the solar system, the problem wouldn't be observing a light in the sky. It would be surviving its consequences. The damage would not have to begin on the surface. It could begin above, in the atmosphere. The radiation from a nearby supernova would alter chemical processes that normally protect terrestrial life, invisible balances, delicate atmospheric layers, mechanisms that we rarely perceive but upon which the biosphere depends. If part of that protection weakens, the surface changes slowly. The oceans receive more radiation. Ecosystems begin to strain. Biological chains lose stability from their smallest levels. It would not be an instantaneous destruction. It would be a planet discovering that its equilibrium was always more vulnerable than it seemed. After such an explosion, the universe does not stop. The wave continues to expand. The debris begins to cool. The light keeps traveling. What for a planet might have meant a crisis, for the cosmos is physical continuity. There is no warning in space. There is no intent, only matter dispersing slowly. The type Ia ceases to be a detonation and becomes an energetic footprint, drifting forever among the distant stars of the void. And while its remnants drift through the infinite reaches of space, all the other galaxies continue to move, following their path with an absolute and quiet sense of normalcy. Silence, finally, returns to the deep and eternal dark. Type Ia supernovae helped us measure the universe. But they also reveal something far more uncomfortable. Life does not exist separate from the cosmos. It exists within it, under its physical laws, depending on distances that are extremely and dangerously precise. An explosion can become a scientific tool if it happens far away. That same explosion could alter a planet if it occurs too close. That difference sustains a large part of our stability. Not an invisible barrier. Not a special protection, only astronomical equilibrium. And perhaps one of the most profound ideas of observing the sky is to understand that human stability has always depended on cosmic conditions that are very, very specific. Somewhere in the universe, a dead star can be transformed into light. That light can measure galaxies. It can reveal the vast expansion of the entire cosmos. It can also remind us just how fragile a living planet can be. The Earth does not remain stable by force. It remains stable because of distance. And in the silence between the stars, that distance remains enough